one side of the spinning ball is faster than the other, which leads to the pressure difference. This ball is shown to be without the spin. Now, if you spin it, there is faster air here. You see, this is the same direction as the air, ball is spinning in this way direction. Faster air, lower pressure, slower air, higher pressure, and this results in the deflection force. Using Bernoulli's principle, we find the speed of flow coming from a spigot on an open tank. Pressure is same, whole of the liquid is there. So, half rho V 1 square plus rho g y 1 at this point. On the top velocity is 0 also. So, it is equal to rho g y 2. You can find out the velocity, it is under root 2 g h, where h is the difference between this position and this position of the pipe. So, it is 2 g y 2 minus y 1 under root. This is called Torricelli's theorem. Venturi meter is another application of Bernoulli's theorem. It is used to measure fluid flow by measuring the pressure difference. Atomizer जो सेंट वगैरह तुसीं यूज़ करते हो उस दे विच स्प्रिंग पंप होया करता है, एक साइड ते रबर बल्ब है. When the rubber bulb is squeezed, the air blows in the tube T. The air blows here. When you squeeze it from here, the air blows from here. It blows with high speed, and according to Bernoulli's theorem, it creates a low pressure here on the top. And this pressure is much lesser than the atmospheric pressure on the liquid surface in the vessel. And due to this, the liquid rises up in the tube and is pushed out with the air through the nozzle in the form of a spray. The same principle is used in a paint sprayer, oil scent and nasal sprayer. Similarly, in Bunsen burner, the gas escapes through the fine nozzle N with a high velocity. Gas flows through this. It results in lowering of pressure in the neighborhood of the nozzle. Due to decrease in pressure inside the burner, the atmospheric air enters through the hole that hatch. The air and the gas mixture rising up produces a flame when it is ignited. In a storm, thatched houses, kacha houses having thatched roofs, they are blown up because they are light roofs. So, in a storm, sometimes the light roofs of thatched houses are blown off because a high velocity wind blowing over the roofs decreases pressure above the roof. ਉੱਪਰੋਂ ਦੀ ਬੜੀ ਹਾਈ ਵੈਲੋਸਿਟੀ ਨਾਲ ਵਿੰਡਸ ਬਲੋ ਕਰਦੀਆਂ ਨੇ, ਸੋ ਟੌਪ ਦੇ ਉੱਤੇ ਪ੍ਰੈਸ਼ਰ ਘਟ ਜਾਂਦਾ ਹੈ. ਰੂਫ ਦੇ ਅੰਦਰ ਪ੍ਰੈਸ਼ਰ ਜ਼ਿਆਦਾ ਹੁੰਦਾ ਹੈ ਬਾਹਰ ਨਾਲੋਂ, and because of this difference of pressure between inside and outside the house, the roof lifts it, the pressure difference lifts the roof upwards. This is again Torricelli's theorem here. If there is no change of pressure, P 1 plus rho g h 1 plus half rho V 1 square equal to P 2 plus rho g h 2 plus half rho V 2 square. Top the upper velocity 0 है, below you have pressure P 1, as the pressure is same and velocity, let us take it to be V here, then we have derived this already, Torricelli's theorem. V is equal to under root 2 g y 2 minus y 1, or you can say 2 g h, where h is equal to y 2 minus y 1. Here it is taken to be h 2 minus h 1. This is the velocity that is shown here. You see, maximum range is in the middle. If you have hole equidistance above and below, middle to above the below अगर बराबर दूरी दे उत्ते holes कर देतियां जान, then these holes from the water from these holes will have the same range, same horizontal range. Now, let us talk about viscosity, the property of a liquid due to which it opposes the relative motion between the different layers is called viscosity or fluid friction. Viscous force is directly proportional to the area, directly proportional to the velocity gradient, or F is proportional to area into velocity gradient. Velocity gradient means change in velocity with distance, or F is equal to some constant eta a dV over dx with a negative sign because it opposes the motion. You can also define it as shearing stress per rate of change of shearing strain. SI unit is poise, CGS is poise, SI is decapoise. 1 decapoise means 1 Newton second per meter square, and 1 poise is 0.1 Newton second per meter square. George Gabriel Stokes is the name of an Irish born mathematician. He worked most of his professional life describing fluid properties, and his most significant accomplishment was the work describing the motion of a sphere in a viscous fluid. This work led to the development of Stokes' law, a mathematical description of the force required to move a sphere through a quiescent viscous fluid at specific velocity. When a spherical body falls through the fluid, layer in immediate contact with it sticks to it and moves along with the body with the same velocity. The layer next to it has lesser velocity, the layer still next to it has still lesser velocity, and so on. And if the layer is at a far off distance, at a large distance from the body, that layer remains at rest. Means the layer of the fluid just in immediate contact moves along with the body. Because of this relative motion, a backward dragging force is set up, and this dragging force opposes the motion of the body. This backward dragging force is called viscous force. As the body falls, its velocity goes on increasing, and likewise the viscous force on the body becomes equal to the weight of the body. ਜਿਉਂ ਜੋ body fall ਕਰੇਗੀ medium ਦੇ ਵਿੱਚ, ਉਹਦੀ velocity ਵੱਧਦੀ ਜਾਏਗੀ, and at a certain stage जो viscous force है, viscous force opposite direction ਚ ਹੁੰਦਾ ਹੈ motion ਦੇ, viscous force becomes equal to the weight of the body. Then at that time the body starts moving with a constant velocity, which is called as terminal velocity. Stokes found that when the body attains terminal velocity, viscous force on the body is given by F equal to 6 pi eta r b. What is eta? Eta is coefficient of viscosity. What is r? R is the radius of the spherical body. And what is v? It is terminal velocity of the body. This relation 6 pi eta r v is called Stokes formula. To derive Stokes formula, we have to assume certain things. The medium through which the body moves is of infinite extent. Moving body is perfectly smooth and rigid. The medium that is being taken should be homogeneous and continuous. There is no slip between the body and the medium. The flow is steady and streamlined. Flow streamline होना चाहिए, body slip नहीं करनी चाहिए medium दे नाल, medium homogeneous और continuous होना चाहिए, और जो body है perfectly smooth और rigid होनी चाहिए है, and the medium should be of infinite extent. Stokes found that viscous drag depends upon three things: coefficient of viscosity, velocity of the body, and radius of the spherical body. We can use dimensional analysis to derive the relation between F, eta, V and R. Let us say F is proportional to eta, eta means coefficient of viscosity to the power A, velocity to the power B and radius to the power C. Dimensions of F, ml t minus 2, eta ml minus 1 t minus 1, velocity L t minus 1 R L. There is only one m to the power A, L to the power minus 1 into A, L to the power 1 B plus B, L to the power 1 C plus C. So, L to the power minus A plus B plus C. There are two t's here. Here it is minus 1 into A, power of t here is minus A, here it is minus B, it is minus A minus B. Equate the powers of m, L and t on both sides. Power of m on right hand side is A, power of m on left hand side is 1. So, A is equal to 1. Put this value in minus A minus B equal to minus 2. You get B equal to 1. Put the values in A and B in this equation, you get C equal to 1, you get F equal to K eta R B, or F is equal to 6 pi eta R B. This 6 pi is found with experimental results. So, dimensional constant here it is 6 pi. So, F is 6 pi eta R V. Then what is terminal velocity? When a spherical body falls through a viscous fluid, it experiences a viscous force. The magnitude of the viscous force increases with increase in velocity of the body falling under the action of its weight. As a result, the viscous force soon balances the driving force and the body starts moving with a constant velocity. This constant velocity with which the body falls when the viscous force has become equal to the weight of the body is what is called terminal velocity. So, you consider a spherical body of mass m and radius r. Let density of the material is rho and density of viscous medium is sigma and let coefficient of viscosity is eta. As the body falls, the three forces that act are weight, spherical body the volume है 4 by 3 pi r cube और density ऐसी रो ली है तो मास कितना हो गया volume into density 4 by 3 pi r cube rho g. Upward force, buoyant force is 4 by 3 pi r cube sigma g. So, effective weight is how much? Weight minus upthrust, mg minus u, u stands for upthrust or you can say buoyant force. 4 by 3 pi r cube rho g minus 4 by 3 pi r cube sigma g. So, mg dash equal to 4 by 3 pi r cube rho minus sigma into g. The viscous force is acting vertically upwards. Viscous force goes on increasing. A stage comes when weight of the body becomes just equal to the viscous force. क्योंकि वेलोसिटी बढ़ती गई विस्कस फोर्स भी बढ़ता गया एक स्टेज ते जाके विस्कस फोर्स वेट के बराबर हो जाएगा. एट दिस स्टेज द बॉडी स्टार्ट्स फॉलिंग विद द कांस्टेंट मैक्सिमम वेलोसिटी व्हिच इज टर्म्ड एज टर्मिनल वेलोसिटी एंड फ्रॉम स्टोक्स लॉ विस्कस फोर्स इज 6 pi eta r b. So, net weight 4 by 3 pi r cube rho minus sigma into g is equal to 6 pi eta r v. Then v is equal to 2 by 9 r square rho minus sigma into g upon eta. So, this is the relation to find out velocity. This equation is the expression for terminal velocity. If the density of the medium through which the spherical body falls is very small, then density of medium may be neglected as compared to the density of the material. You get velocity as 2 r square rho g upon 9 eta. So, sigma can be eliminated from this term. So, at a certain standard viscous force which balances the downward force, that is weight of the body starts falling with constant velocity called terminal velocity. So, this figure shows you different forces, buoyant force, this is viscous drag and gravity. Buoyant force ऊपर नो, viscous drag भी ऊपर नो, gravity नीचे नो. You can find the velocity by having a long tube, put a glycerine in this, have a small spherical ball to fall through the liquid column. The viscosity of liquid decreases when you increase the temperature. As the temperature increases, viscosity decreases. शहद ਨੂੰ ਗਰਮ ਕਰੋ, शहद पतला पै ਜਾਂਦਾ है, means उसकी viscosity घट गई है. Viscosity of gases increases with increase in temperature. Note this point. In the case of gases, the viscosity increases with increase in temperature, whereas in the case of liquids, viscosity decreases with the increase in temperature. What is the effect of pressure? Lubricants viscosity increases with pressure. As pressure increases, viscosity increases. For most lubricants, this effect is considerably larger than the other effects when the pressure is significantly above atmospheric pressure. The Barris equation is given as eta rho equal to eta naught e the power alpha p. Alpha is the pressure viscosity coefficient and p is the pressure of concern in pascals. So, today we learned about fluid motion and viscosity. Thank you.